Okay, in this video segment, we're going to talk about metals, nonmetals, and metalloids, and kind of how we find them on the table, and also some of the properties that they may have. So when we look at the periodic table, we see that our metals are the bulk of the actual elements on the periodic table. They span everything from group 1, your alkali metals, all the way through the transition metals and the metals under the stair-step line. And again, we have this extra row now that a lot of the old periodic tables don't show. So imagine this stair-step line coming down in here, and then we're actually just going to carry it straight down from here, and we'll keep the halogens all in that non-metal kind of category over here. Okay, and then also your intertransition metals down here, also your metals. So all of this stuff is metals, and then what we have is on this side we have this kind of orange area. These are your non-metals. Okay, so on your periodic tables, if you don't have this, go ahead and draw this in, where start between boron and aluminum and kind of draw in this dark line and go down over, and almost stair step your way down. And then when we get here, it really doesn't matter if you go straight down or if you go over and down. We don't know enough about these elements anyway to really determine their metallic characteristics. So I won't ever ask you about these last few elements in terms of if they're metals or non-metals. So really this is the point that you got to end it. But you can, if you want, either slide it straight down or move it over one more and down if you need to finish out your staircase. So these are your metals over here, and then you have your non-metals in this region. So the majority of our elements are metals. We do have a bunch of non-metals, and then these purple ones sitting on this chart right here, these are considered metalloids. So they have some characteristics of metals, some characteristics of non-metals. But they're not one way or the other enough to actually classify them as a metal or not metal. So we give them this term metalloids. A couple to note in particular, right here, this is aluminum. So if you take a look, aluminum is number 13 on our periodic table. Notice how it sits on this stair-step line with the rest of the metalloids, but aluminum is not considered a metalloid. Okay, so make a note of that in your notes, make a note of it on your periodic table or someplace. Because it is one of the metals that touch this stair-step line that are not metalloids. Okay. Besides that, everything that touches this stair-step line is considered a metalloid. Sometimes polonium number 84 right here is also considered a true metal and not a metalloid. Again, it's not one I'm going to really test you on. But the aluminum one is one I do need you to remember. This is not a metalloid. That aluminum is truly a metal. Okay, in terms of our different elements. Now, when you start talking about metals and nonmetals, like what makes them a metal, what makes them a nonmetal? Well, we have a chart. Now, there's more properties than just this, but these are the ones that are really easy to identify. Okay? And the first one is probably your most common used property to identify a metal versus a nonmetal, and that has to do with conductivity. So if you are a metal, you are good at conducting electricity and you're good at conducting heat, all right, so, or heat energy. Nonmetals tend to be very poor conductors of electricity or very poor conductors of heat. To give you a comparison, the worst metal is still over 100 times better than the best nonmetal at conduction. So there's a huge gap between metals and nonmetals in terms of how well they conduct electricity. Now your metalloids, those are your semiconductors. Probably the most famous of these is silicon. So silicon is one of our metalloids. We actually utilize that concept or that property of silicon to be a semiconductor in all of the computers that we have in the world. So all computer chips right now are made out of silicon for the most part, and silicon's ability to semiconduct or for our ability to control the conduction of silicon is one of the key pieces to building computer chips. So it's a key property of that one semiconductor or that metalloid that actually is helpful for us in our world. Now, another key property that we tend to see is that metals tend to be malleable and ductile. Malleable just means bendable, and ductile means the ability to draw into a wire. So you can bend and shape metals pretty easily, and you can actually form them and extrude them into wires really easily. Nonmetals tend to not be very malleable. So think of like sulfur. Sulfur is a nonmetal, or phosphorus is a nonmetal, or iodine. They're all nonmetals. They tend to be really brittle. They break and they crack and that kind of stuff if you were to hit them with a hammer. Whereas metals, if you hit them with a hammer, they tend to dent. So they tend to be more malleable and ductile. Metals you can shine to a high luster, so they look shiny to us, whereas nonmetals tend not to. Metals almost always lose electrons when they ionize, so they end up being positively charged, whereas nonmetals tend to gain electrons, so they're almost opposite of each other. And then metals tend to corrode. So if you look at metals, they tend to combine with oxygen pretty easily and to corrode or to rust, basically. And then in nonmetals, a lot of our nonmetals form those diatomics that we talked about before. So instead of corroding or rusting and attaching to oxygen, they tend to bond with themselves if they can, forming diatoms or diatomics. Even some of the nonmetals like sulfur and phosphorus actually form polyatomics, which are groups of 6 and 8, or these big, huge circular molecules of themselves also. So they tend to bond with themselves when they need to. Now, if you look under metalloids, all this stuff is kind of variable. So for metalloids, besides this ability to semiconduct, you really don't have good information about the metalloids because each one is so unique and individual that you can't give it a classification. But the easy thing about metalloids is they tend to do a little bit of both. So they might have something it might be malleable, but no luster to it. Or it might lose electrons, but also form diatomics. So it might have some properties of metals and some properties of nonmetals. Okay? This will be a good distinction for us later on in the year because we talk a lot about what metals do in terms of bonding versus what nonmetals do in terms of bonding. And then, of course, we kind of throw those metalloids in whenever they need to in that process. So that's another way for us to actually classify things on the periodic table is by metal, nonmetal, and metalloid. Now, when we look at the periodic table, we need to start talking about ions. And we talked a little bit about them in our last unit, but we want to make sure we have them officially into our notes now. So ions are a form of an atom that's lost or gained an electron. Okay, so an atom we say is a neutral particle. An ion somehow has become a charged particle, gaining electrons or losing electrons. If we have a positive charge, we call that a cation. That comes from losing electrons, so that's typically your metals. If you have a negative charge, that's from gaining electrons. We call that anions. Those are typically your nonmetals. Now, remember, cations and anions, there's lots of different ways you can do it. I used to have, in college anyway, I used to make up a story about, I had a friend her name was Anne. She tended to be more of a negative person in my life, so that helped remind me that anions were negative. People who are cat lovers, maybe because it's a cat for cation, that's a positive thing in your life, and you remember that being positive. I'm allergic to cats, so that would not work for me. However, cations does have a T in it, and T looks like a plus sign to me, so that might remind me that cations are the positive ones, and anions, or like anti or negative, are negative ones. So however you need to remember that one. Now the cool thing is, the periodic table can actually guide us in terms of some charges. Not for everything, but for certain ones. Okay? And I'm going to show you these here in a minute. One thing you need to remember is that you may have been given a similar guide in previous science classes like earth science or middle school science. And they tend to do more generalizations than I want you guys to do. Okay, so I'm going to limit this a little bit more than you probably have seen before. So if you look at your periodic table, and if I was you, I would actually write these right on the periodic table, someplace where you can remember it and go and look these up. If you are an alkali metal, so all your alkali metals, they're going to be a +1 charge, always. They have one extra electron, so they dump that one extra electron. Hydrogen can be a +1 or a -1, so it can do both, depending on how it wants to ionize. So it's not like the alkali metals, it's a little different. Your group 2 elements, your alkaline earth metals, are always a +2 charge. Okay, so group 1's a 1+, group 2 is a 2+. Now the transition metals in the middle here, they form all sorts of different ions. They're always positive, so you could say a plus sign for all these down here, because transition metals are metals, so they're going to be a positive ion. So they will always lose electrons, but you can't use the periodic table to determine what it will be. Once you jump over to the P group, or the P block of our periodic table, we get to group 13. Now group 13, if you're boron or aluminum, these first two, you only form a 3+. As soon as you start getting into the P elements that also have a d orbital available, then their charges become variable, which means in this first column you can be a 1+ or a 3+. If you are a non-metal or a metalloid in group 14, we don't know what the charge is going to be. You can't designate it. You may have had teachers in the past who said +4, -4, +2, -2. The reality is this is carbon and silicone. Carbon and silicone don't really ionize. So carbon and silicon tend to only share electrons. They don't really ionize very often. So giving them a charge is really not a proper thing to do. However, below the stair-step line, the metals and metalloids down here below that, when they do ionize, do so as either a +2 or a +4. Once you get over to group 15, now you're starting to deal mainly with nonmetals. So the nonmetals form negative ions. So in group 15, things like nitrogen and phosphorus and arsenic, if you're above the stair step, you're going to be a -3 charge. So these will all be -3 charged. However, if you are a metal below the stair step, like bismuth and antimony, you can either be a +3 or a +5. So you can ionize to a +3 or +5. Okay. Now, after this point, everything else kind of goes back to regular because we're starting to deal with these oxygen group and then your halogens and your noble gases where they ionize very specifically. So oxygen and everything else below that in group 16 always forms a -2 charge. Okay. Halogens and everything that go down the halogen group, remember that's just this group 17, they always form a -1 charge. And then your noble gases do not ionize at all. Noble gases tend to not bond in general, but they do not ionize. So if they do ever form a compound, it will not be through ionization. Okay. Now what this does for us is kind of nice. Alkali metals +1, alkaline earth metals +2, oxygen group -1, halogens -2, noble gases are 0. Those are all pretty set. A little goofiness in here, but we can talk about that as we go through in our bonding unit, next unit. Okay. So great thing that the periodic table does for us, it allows us to start to map out this ionization a little bit for our ions. Okay. Now we're going to jump to the board and take a look at why would we get these doubling effects down here. Why would we get more than one charge in some of these areas? Okay. Okay, so if we take a look at group 13, and let's pick one element out of there, let's say indium. Okay, so indium, if we take a look at indium, it's number 49 on the periodic table. And if we do its electron configuration, it's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then it's a 4p1. Okay? So if we take a look at what is going on with our indium in terms of ionization, well, it's not going to ionize anything through here because these are all 1s and 2s and 3s in terms of its orbitals. It's not going to ionize here because that's again a 3. So your 1s, your 2s, your 3s are all safe. No ionization there. That's not the outer energy level. However, we do have two different sets of electrons in the 4th energy level. And if we look, if indium is going to be a 1 plus, well, it can just take away this electron here from the p orbital. If it gets rid of this electron from the p orbital, now it has everything full. So if it has everything full, that's a stable configuration for it. So becoming a 1 plus works really well because it ends up having everything full for its orbitals, getting rid of this kind of partially full orbital. But indium can also become a 3 plus. Because even though this is a full orbital, wouldn't it be great if we got rid of the 4th energy level altogether? So what can happen is you have a full 1, a full 2, and even your 3rd energy level with that D is completely full. So by ionizing to a 3 plus, again getting rid of these electrons, you also have an advantage in terms of stability. Now, the same thing that we just talked about with group 13 with the +1, +3, you can apply to group 14 and group 15. So within group 14, you can do a 2 plus to empty out the p orbital or a 4 plus to empty out both the p and the s orbital. Same thing over here, where the 3 plus would empty out the p orbital and the 5 plus would empty out the p and the s orbital. So in all cases, they're basically ionizing here to remove the s and p electrons and only leave those d level electrons so they have a full energy level at the end. Okay guys, that ends this video. Thank you.